So today we have Alfred Vollmer. We do co-work on the meeting today. Alfred is now part of my team, and so we will alternate in putting the questions out. And here is Alfred, and he can do a quick introduction, which I also like from the three of you for the auditorium, that they know where you are from. And yeah, here we go. My introduction is, I'm Bodo, I'm still around, and I'm still in my office, and my kids like it that grandpa is coming in and being available every now and then. So, Alfred, give a little introduction.
I'm Alfred Vollmer. I'm German. I'm located in Munich. So while Bodo is located in the north, in the very north of Germany, I'm located in the south. And in order to help Bodo a little bit, that he can spend time with his grandchildren, I came on board. And that's why I will be supporting you. I'm now the editor-in-chief of Bodo's Power Systems. I suggest that we just start, and maybe Ehab, you can introduce yourself, and then we will go ahead with Markus, with Daniel and Brandon.
Yeah, so my name is Ehab Tarmoon. I'm an SME, that's a subject matter expert in the silicon carbide business unit here at Microchip. And I'm based out of our Novi, Michigan office, which is a suburb of Detroit. I'm glad to be here today. Thank you.
Okay, very good. And Markus? And Daniel, I'm sorry.
No problem.
You're too close to me. You're just 5 kilometers away.
Yeah, I know. No problem. All good. Daniel Makus, I'm heading the application department for the XCV power conversion for different technologies. So basically, we are responsible for any kind of conversion which makes sense, which really innovative everything. So that's my task, to organize all the solutions for our customers. So. And SiC, yeah, I have a double meaning of SiC. I'm personally a little bit sick today, but I think the topic is SiC. That's fine. All right, happy to talk to you guys.
So we even appreciate it more that you participate today while being sick, talking about SiC. Yeah, and Brandon.
Yeah, thank you very much. So good afternoon and good morning to everybody. My name is Brandon Becker. I'm the marketing manager for our SiC power device solution business at Qorvo. And I am working in the Dallas-Fort Worth office and reporting into our Dallas office. And then we have a big development team here in the US and New Jersey. So, and if you don't know, the Qorvo silicon carbide team was the acquisition of United SiC a few years ago.
Yeah, the former company is well known to us, and we had a lot of history at that point. Anubala and I worked once for Don Berg in Mountaintop, Pennsylvania. That's a while ago.
Yeah, it's a small world. Always is.
Okay, we are at the point that questions could reach the experts. So that question is addressed to Infineon. The power conversion in automotive is under strong evaluation, new requirements, use cases under strong cost pressure are shaping the challenges of designers. On the other side, the solutions become very fragmented. New technologies, packaging options combined with integration solutions. Are there some clear positioning recommended in the near future? Again, where will be SiC dominate, where GaN gains the momentum, and why? That's a general big question.
All
to
right.
Makus.
Good. No, very complex question, but I think it's all what our customers, our strategies are now all about. Yeah. Well, what we see is of course a lot of knowledge gain in automotive power conversion happening. If I compare maybe 5-10 years ago, automotive business, the power conversion itself was in the range where typically power designer will say it's a power dissipation of my gate driver. You know, now they start really to design massively since a couple of years a kilowatt of power conversion running at hundreds of kilohertz. But before they start to ramp up, the cost pressure increase already like hell, right? So interesting point is here really the solutions, right? So it all starts with technology, but not always ends with technologies. That's why the question of positioning of technologies always I would like to link with the use cases customer really want, because if I look today's market and maybe recent dynamics in markets are showing already what happens. We started with high end to make everything super dense, everything super efficient. And by the way, if I compare automotive first DC-DC OBCs, which started in production, we've been already at the level of 93, 94% efficiency, where maybe the solar guys and the telecom guys at the beginning were dreaming about that. So we started already very high. So systems were already super efficient. But nevertheless, I mean, we want to, or our customer want to make it smaller, right? Smaller, less weight, less material. All these new regulations are coming. That's why I would really answer in the way. So it really depends on a customer use case. If we talk about silicon carbide, it's a beautiful technology. There's a lot of flexibility given. So we have voltage flexibility. I think all colleagues here from the market can only confirm that the flexibility of the breakdown of the silicon carbide makes this, especially for high voltage conversion, really easy to use. And this is actually also in combination with thermal capability and robustness of silicon carbide. Thanks to our colleagues in the industry, photovoltaics and similar, is already proven. That's why I would say if we talk about silicon carbide, is very clear direction, harsh systems, optimization, scalable system, high voltage. Maybe 800 volt is linked to silicon carbide today because it's easier to implement, right? So if you compare to gallium nitride, well, we're just at the beginning. The beauty of technology, everybody knows, all the switching, optimization, super small devices, integration capabilities. This gives us new ways to implement the power conversion. And at the same time, you know, if I really stick with automotive, this is a market which is not often known for super fast in innovation. But in order to get the gallium nitride there, we need really to start innovation. And this is, I would say, sometimes a dilemma on the customer side to take gallium nitride already now and utilize it, but maybe products are not completely ready. Maybe topology I use are not optimized. That's why the innovation, if we talk about the future, new topologies, packaging technologies, this is the way to go. And where gallium nitride is, of course, giving a lot of new options. And maybe easy positioning would be, at the moment, in direction where size matters, and size and efficiency matters. that is the beauty of gallium nitride. And I would even prefer, if I take the next generation designs, to combine both. So because there are beauties of silicon carbide, which you can use, for example, in a PFC, super robust, a lot of nice attributes thermally, and the fast speed of gallium nitride, and then you have a beautiful design. So you have all switching capabilities of gallium nitride, maybe in a DC-DC stage, and you have a robust technology in a PFC. Designers would love that.
Thank you. Any cross questions between you? And if not, I would say we can switch to the next question. And Alfred, you go.
Okay, the next question goes to Microchip, so to Ehab. Would you please briefly describe the applications of a battery disconnect switch and the benefits of solid-state technology over electromechanical solutions?
Yeah, sure. So the first application that comes to mind is EVs, electric vehicles, and plug-in hybrid electric vehicles. In the battery packs, you have a unit called a BDU, a battery disconnect unit. And what that has is fuses, pyro fuses, contactors, basically providing the power feed to the rest of the electrical distribution system in the EV. Some of the biggest challenges today with that technology is the reliability. So we're talking about solid-state solutions using silicon carbide as a battery disconnect switch. Great performance, but the biggest driver, when you talk with OEMs, the biggest reason for interest in the solid-state approach is the poor reliability of the existing solutions. So many issues, it has among the highest fit rates. So when you look at a solid-state solution like a SiC-based high voltage battery disconnect switch, some of the benefits is that you have the fast response time. If you look at consider a short circuit event in an EV, it can reach tens of thousands of amps, 20 to 30,000 amps during a short circuit. So very high lead through currents, high energy going through the wiring, through the loads. With a solid-state solution, you're able to respond very quickly. And with that fast response time, you're now able to limit that lead through current to, instead of tens of thousands of amps, to maybe 1,000 amps or 2,000 amps. And you have that control of exactly where and how fast it responds. And that has a lot of benefits, like I mentioned, in terms of lower lead through current, lower lead through energy. And another big benefit, and there's many, but another major benefit is the being solid state means that it's resettable. A fuse, a pyro fuse, it's just a one-time trip device, whereas a solid state solution like a SiC-based eFuse or a battery disconnect switch is resettable. And that alleviates a lot in terms of the system design. All the design for serviceability constraints are gone. You don't need to worry about making it accessible and serviceable. And then all the reliability issues related to the components that allow it to be accessible, all that is gone. It really simplifies the vehicle packaging, and that's with EVs. And if you look at other applications that are battery powered, same thing. It really simplifies the overall system design, architecture, packaging. So those are a couple of the major benefits, and there's many others as well.
And I think regarding the point that it's resettable, it's also very important when it comes to highly autonomous driving, the higher levels. You cannot just shut off the car in the middle of the highway running at 70 miles per hour. You have to find a safe way to the side of the road. And this needs to be guaranteed. And you can handle that with a resettable fuse.
Yeah, and if I can add on to that, you know, with a fuse, it's not tripping based on the current. It's tripping on the energy that is in the temperature generated from that current. Whereas with a solid state approach, it's measuring the current directly. It's not assuming what the current will be with a lot of error in that. So you have very precise control of the behavior of the system.
And you mentioned that it's much faster. Maybe you can give a number, the order of magnitude, how much faster it is.
Yeah, so if you look at relays, contactors, they're in the milliseconds, several milliseconds range, maybe up to 10 milliseconds range. Fuses, same thing, about a millisecond or more. And then you talk about pyrofuses, the fastest that I've seen with pyrofuses is 500 microseconds. And that doesn't include the communication and the detection and everything else. Now, if you look at a system with very high voltage, say 800 volts or 1,000 volts, low inductance, which is very likely, the current's going to shoot up very quickly. And so within a few microseconds, it'll reach, so within 20 microseconds, a system could reach 20,000 amps. With a solid state solution, you can design it to respond as quickly as you want. We have an eFuse demonstrator, a lower current eFuse demonstrator that responds in under 700 nanoseconds. And it's configurable. So in the software or over the LIN bus, you can configure how fast it responds. So you have that control exactly how fast. And you can even switch it faster than that. So if you understand the amount of inductance in the system, you can design it for a certain trip current. And that way you guarantee it will not allow more than X number of amps downstream in the wiring and the load.
And you mentioned relays as a competitor. We talked about the timing, which is a really, really, really important issue. But in relays, you have a very low, so to say, on resistance. Could you please talk about that aspect, how it refers to each other?
Yeah, I want to say it's no comparison when you look at the resistance of a relay or a contactor versus a solid state solution, right? With solid state solution, you have to put devices in parallel to achieve an overall lower resistance. A contactor will give you much lower resistance, but it has several other challenges with that. It requires a lot of additional components in terms of when you close the contactor, you have to make sure that there's no more than around 10 to 20 volts across it. Otherwise, you risk welding it shut. You have to characterize it properly with the load, and it has a certain number of cycles it can handle. So you look at the mechanical cycles, which usually is very high, but then under load, under electrical load, that number comes down significantly. And that's under normal conditions. During a short circuit, most contactors are just going to weld shut. And that then presents a hazard. So now you have high voltage on the wiring, and you take your vehicle in to get serviced, it's live. You have 800 volts on the wiring on the connector. And that can also be a safety concern.
Is there any regulation concerning that trend already in place? Because, automotive is super driven on regulation side to get the innovation in, and I guess this is a safety related topic somehow. Do you have any trends in this direction coming from maybe some standardization gremium and stuff like that?
Yeah, so I've seen with ECE Reg 10, I believe, that has talked about galvanic isolation from the high voltage system to the low voltage system. But within the high voltage system itself, I haven't seen any requirements, any regulations. It's more, each OEM has their own requirements. So the trend that I've seen is, if you look at the battery disconnect unit, you have two contactors. You have the positive contactor and the negative contactor. And the trend that I've seen is to have one of them remain as a solid state, or one remain as a contactor, and the other one to go to solid state. That way, the contactor can provide a true open circuit, whereas solid state devices are going to have some leakage current. But you're using the solid state device to make and break the circuit. The contactor won't be responsible for making and breaking the circuit. And that will extend the life of the contactor, improve the overall system reliability with that approach.
But
nice.
You mentioned servicing, but the manual service disconnect, the MSD, I think it will still remain in the car, or am I wrong?
when you remove the MSD, then that should de-energize the high voltage system, to the rest of the vehicle, typically.
So this still remains mechanical, but you have to open the hood for it.
Yeah. So the contactor is inside the battery pack. It's in the BDU, which is in the battery pack. So now you have to drop the pack from the vehicle, which is a big undertaking, right? It requires, first of all, somebody who is trained to work on high voltage, so a qualified technician with high voltage, and then trained to work on that vehicle to know how to drop the pack. And then you wouldn't replace the contactor, you'd replace the whole assembly, the whole BDU. So that's going to be, costly in terms of service, and, the actual parts themselves, the labor and the parts.
Okay. Thank you, Ehab. But I think Bodo has got a question right now that he wants to get answered.
I'm not.
Not yet?
You need to trigger my.
Okay.
We have an electro vehicle.
No. I thought you have the question to Qorvo.
Okay, now the question is here. I misunderstood you, Alfred.
Sorry about that.
It took a moment until it popped up on my screen. So the question is addressed to Qorvo. What does Qorvo see in the future of solid state circuit breaker applications?
Yeah, so I think this is a perfect piggyback off the battery disconnect unit, right? The battery disconnect unit is a type of solid state breaker, right? Changing from mechanical to electrical. But I think we see that at a much grander scale, like just across the world, right? So if you look at what's going on globally, right? Heat waves and energy distribution and power plants, and I've seen it, in the US and in Europe, and there's a lot of demand on our electrical grids. And so I think that there's a big push to understand, hey, how can we move this from industrial buildings, to service an electrical or industrial building? There's a lot of safety requirements that go in when you're trying to pull and shut off power to those buildings. There's thousands of amps that are running through there. It's very costly, very expensive. So there's a lot of interest to, hey, what can we do from a solid state solution to even servicing buildings? I'm seeing fleets, right? So fleets of electric vehicles, like Amazon, for example, they have to have tons and tons of charging stations, and they need a way to be able to protect that charging station and be able to disconnect it from other parts of the buildings. And then even at the residential level, right? There's a lot of being able to have on-demand energy of loading air conditioners and turning off appliances during peak and non-peak times. And so all the way from the biggest of thousands of amps all the way down to 30 amp, 20 amp, 15 amp breakers in residential, there's a big push in these applications to see how we can take them from mechanical solutions to solid state solutions. So again, programmability, the high power requirements, the functionality, all those are playing a huge role in those applications.
Exactly what I also see. Smart meters are just starting to come to the end user in combination, as you said, monitoring for peak. So taking the best opportunity, bringing it together with solar, and so using the advantage to take power from the consumer when it's needed and give it back when there is excess in the grid. So that's absolutely what I also see, and I myself have moved quite a bit forward to that direction, having solar, having storage, having a wall box, and have the electric car. So that together brings quite a nice combination, together with a heat pump that makes the little environment at my house very, very efficient. But switching fridges when the peak is, and heating up when the peak is, and not when the peak of delivery of power is, and not when the peak of cost is. Yeah, that's a really, really big market ahead of us for these.
It's a big shift. It's not only a shift on one application, and I think it's a shift on really just how we're building out cities, right? How we're building out industrial centers, how we're building out residential places. So it's really a huge shift just fundamentally. And being enabled by these, silicon carbide and even GaN in some places by these technologies, being able to reach higher temperatures, being able to reach higher currents, the robustness, and so forth, all these properties that we're getting.
Yeah, the modern semiconductors, the SiC devices make it happen. About 40 years ago, I used in my house Crudum or Cridum relays. Most people will not know about them. They were based on trioctyrostor, and they just were good for turn on and turn off. And you could, I still have two in place in the house, but no longer active, just to turn on lights. And that was 40 years ago, some kind of experiment I did. I was able with TTL logic to drive these electronic relays at the mains in the house. Okay, that was just a memory.
I can add a little to this topic. It's very interesting. So, Brandon, you mentioned charging fleets with Amazon and others, and Bodo, you talked about smart meters. So, one of the benefits of this, of having a smart system like this, is that the overall infrastructure can be simplified. You don't need to set up a very high-powered transformer feeding a building to cover the worst case. Instead, you could have dynamic profiles going to each of the different charging stations and circuit breakers to control and maintain the loading in the system. So you don't need to design and pay for that worst case, loading.
Absolutely. The power lines could kept in a limited space or size. At the moment, everybody is crying for more 110 kV connections, or even the DC links in Germany from the north to the south to bring the wind power down to the south. But smart handling in any kind of applications can help reducing the overall peaks in the power usage. Thank you. Any additional comments? Then I will turn it to Alfred, and we will see the next question.
Okay, so the next one is a longer one. The system cost roadmap is one of the key differentiations in selection of potential solutions. And very often this is a more important issue than the innovation itself. How do you see the innovation adoption in the power conversion? A question to Infineon. In other words, will cost pressure slow down the innovation or even revert the direction to the well-known solutions from the industry?
Right, it's a tricky one. So, all right, yeah, I think innovation is always connected to cost somehow. Sometimes it's even saving the cost, like my colleagues from industry already highlighted. Introducing the innovation in those examples, solid state breakers, reduce the maintenance costs, and all these new use cases would not be easily available if we don't go that way. That's why often the discussion is how much innovation is really simplifies the problems on customer side, and if there's real benefits already quantifiable. Yeah, and this is often a big issue to bring the innovation in high volumes, because it works in the lab properly and is super nice, and the use case makes sense. But finally, the gating actors are often in the purchasing, right? So, and they're all gated to certain market conditions. That's why in some condition, innovation is a good door opener, I would say. So, which enables people to think differently. And there are so many examples from industry where innovation was done 30, 40 years ago, and now is a normal situation, right? So what I expect from a power conversion, due to all the needs, like Bodo exactly said, so we need to stop oversizing the power generation. We need to make sure it's used properly, it's partitioned properly. Maybe we even need to create a profile where we understand how our application or customer's application can benefit with little innovation. So something like profiling, so measuring some power and stuff like that, which we can also implement in on the power semiconductor level, and make, for example, applications which were not really interesting before a main use case. I can immediately touch the topic what I think Brandon said from the charging side, because I was responsible for charging a few years, DC and AC charging, and one of the big innovation there is very much connected to the energy use, so-called vehicle to grid or vehicle to home, and there's so many different vehicle to building, vehicle to anything directions. One of the key issue there is, for example, the business case, right? So how to sell the energy so efficient and maybe also smart, so you buy in energy for free and sell it at the highest price, as an example, to make, for example, building energy consumption very low. This is possible with wide bandgap again, because let's assume we have a power conversion unit, in this case, maybe a DC charger where power conversion is in the charger itself. What happens actually if you start to do such topics, so smart charging, smart energy conversion, is such units are usually designed for full power operation. So for most efficiency at 80%, maybe in some cases even in the little wider range, so like 50 to 80%. But now you operate in like 20%. And you know, most guys who ever designed a power conversion unit will immediately raise their hand and say, wait a moment, at 20%, our efficiency is 70 or maybe even lower. So it's not designed to that way, you know? And this is exactly the bridge to innovation. So now we designed a lot of power semiconductor with silicon carbide, or maybe in future in gallium nitride and so on. And the use cases are often optimized to existing application. And you know, if you save from 96.5 or 97%, another 0.5%, the cost increase that typically purchasing guys see is exponential. It's very normal. It's still the case, We still wait for GaN to reduce all the costs drastically, but it's still not happened so wide. But if you think differently, if we say, look, full power efficiency doesn't matter because 3% or 2% efficiency losses in a power conversion is really negligible because you lose another 20% on cabling anyhow. So improving 0.5% here doesn't really bring you much. But improving in a light load operation bring you 20% maybe. That brings your business case much more prominent. And this is actually exactly the topic. With wide bandgap materials and topologies we can enable with those, the smart energy use become much more interesting. And I tell you, we work a lot with also AC charging companies who request us to optimize the onboard charger efficiencies. And where do you optimize is a light load, because the smart charging or vehicle 1G or there's so many names of such operation, which are in the end of the day light load operation, nothing else. They want to make money with this, and this is how we should really think and connect the innovation, just to understand where innovation is not really just just improve another operation point everybody knows anyhow. Let's think about the new use cases. So, and I think my colleagues already said, so use cases from energy, use cases from customer side, such a robotaxi, for example, where you need to make the vehicle 24/7 operational. And this is the point, because if we always look to the cost, we fail back automatically. And this is maybe one direction I usually bring to discussion with all my customers, but also with partners. And semi world is very small. We know each other. To the other colleagues in the market, let's address the topics which really hurts, and not just improve another 0.5%, which is okay for the designer, but for the complete market is maybe meaningless. This is a topic, what I see at least. I don't know, maybe somebody from you guys from Microchip, Ehab, you guys are also in the power conversion in any kind of directions available. We'll be happy to hear your feedback in that direction.
Yeah, I felt you. Yeah, I agree with a lot of what you said. I mean, it makes a lot of sense. Why focus on that peak power efficiency when most of the time you're not running it at peak power? And an example is with the traction inverter, right? We're seeing that switching to silicon carbide, and there's still some IGBTs now kind of came back, but the IGBT, it has high efficiency at peak power, but then once you drop the lower power, it's not as efficient. Whereas silicon carbide, you have that high efficiency throughout, where the losses are proportional to the current, whereas with IGBTs, they're not. So definitely seeing with silicon carbide, you can maintain that high efficiency over the entire operating range. And then from that, you can potentially simplify the cooling system or extend the range of the vehicle or shrink the size of the battery. So thinking more at the higher level, system level, is good. So I like your example of focusing on that last 0.5%. Okay, what does that buy you when the wiring already has a lot more losses? So that was really a good point to focus on the entire operating range, and most of the time, where is it being used? How for an EV, how often are you accelerating at max acceleration, and for what duration? So does it make sense to optimize for that scenario?
Yeah, I agree with you both, and even to take it one step further, if you look at it, before wide bandgap devices were, really making it to the market, right? You had the silicon, and you came out with like product portfolios, right? But then we had to kind of customize those based on use cases, right? Application use cases. And I think that's happening in wide bandgap as well. It's, a few years ago, it was like everybody, 650 volts, 1200 volts, like you have your just product portfolios that you proliferate. But I think now we're getting to the point where it's like, okay, where are the pain points and what parts of the use cases do we have to improve on? And I think that we're starting to get to the point where it's like, okay, let's make, devices for these certain use cases. And so I see that's a kind of a trend that I'm starting to see that I think all suppliers and colleagues are really working on, which is good to see.
Mm-hmm.
Agree. Yes, absolutely.
Very good answers. Thank you so much, everybody. I think time is running, so we will have to go to the next question, which will be asked by Bodo again.
So that question is addressed to Microchip. How do the advantages of wide bandgap specifically SiC help in the performance of a solid-state battery disconnect switch?
So in this application, it's a battery disconnect, very high current. You're talking about hundreds of amps continuous current and high voltage. And so we talk about a switch that has to block high voltage. It has to have a certain thickness and in order to block that voltage. And so when you go from, if you look at silicon and silicon carbide, there's a few different parameters that differentiate them. And the first one I want to highlight is the electric breakdown field. Silicon carbide has 10 times the breakdown field of silicon. And what that means is that layer within the MOSFET can be a tenth of it when you use silicon carbide. So that has a lot of benefits in terms of faster switching and much lower resistance. And the same thing with GaN. That distance can shrink significantly because of this higher breakdown field. The other benefit of silicon carbide is the thermal conductivity. So with the breakdown field, you can get lower resistance. With the thermal conductivity is 3 times higher with silicon carbide. So you can draw that heat out of the die much more efficiently. So now you can run it at higher current and pull that power dissipation out and the heat out of the die much more efficiently than you can with silicon. And then it's a wide bandgap material. And with both GaN and silicon carbide being a wide bandgap means they can run at a higher temperature and still function as a semiconductor at these higher temperatures. Now, practically speaking, what that means is you can have a higher operating temperature, higher junction temperature, which so you can run it at higher powers, higher current draw, and also higher or a lower leakage current. In some applications where you might need to have like a solid-state circuit breaker, you might need to have an air gap. So leakage current isn't so important in that application because the air gap is there and will block any current, leakage current. But in certain applications, you're not required to have that air gap. And so then the MOSFET, when it's off, it's going to be, it'll have some leakage current. So the benefit of a silicon carbide MOSFET is that leakage current is going to be a lot lower than a silicon MOSFET. So those are some of the 3 characteristics, the breakdown field being 10 times higher, the thermal conductivity being 3 times higher, the band gap 3 times higher. Those are some of the benefits in this application. And there's others as well, but those are the primary benefits.
Thank you. Any questions? So we can go to the next one.
I think it's for Qorvo. Yes, it is, because Qorvo had the cover story in our July issue about revolutionizing circuit protection with silicon carbide JFETs. So the question is, what technology advantage does Qorvo have for the SSCBs?
Yeah, that's a great question. And I think, you have covered a lot of the properties that silicon carbide in general gives us. But you mentioned with the battery disconnect unit, usually, when you're switching from mechanical to solid state, you have to parallel a lot of devices to get that RDS on, that resistance down, right? Because a wire relay versus a semiconductor, it has resistance. one of the benefits of using the JFET technology is a huge contributor of resistance in a MOSFET comes from the gate. And so not having a gate, having a normally on device in solid state circuit applications is a really big benefit. And so that's why we're able to achieve some of the lowest RDS-ons on a single device in the market. And then you also get the other properties of the thermals, right? So when you have a lot of current going through them, a lot of times you don't have room for, you know, heat sinks and liquid cooling. You need air cooling, and a lot of times the airspace is not very big, as was mentioned, and so you need devices that can dissipate heat very, very well. So I think that's the other thing, and then it comes, of course, price, right? We can't take this and convert it all without worrying about price. And I think again, having devices that we're able to achieve low RDS-on at a smaller chip size is enabling us to really work with customers on some of these solutions and have solutions that can actually get into production and then get into real life use cases. So it's exciting to see.
Okay. So Bodo, I think you should get ready for the next question.
I am looking to my backstage. They will send it. It's again to Infineon. We often discuss wide bandgap technologies and their innovation very isolated. With new topologies enabled by further wide bandgap innovations, there will be additional challenges coming and cannot be solved by wide bandgap only. Further system innovation is important, linked to software, sensors, other functional innovations. How do you see that and the importance in the future, especially the software?
All right, Bodo, this is a super interesting question, and maybe I can again continue this story on this light load operation, because it's really something which is very practical example. Yeah. So well, we have super nice material, right? So discuss super small die size, thermal conductivity is a dream. We have a lot of different attributes, such as low switching losses and so on. But then let's start to design the system. We already see immediately, look, the changeover from the well-known silicon-based solutions, IGBT or super junction MOSFET, doesn't really matter, to silicon carbide is already not one-to-one replacement, right? So per definition, yeah. So we have different driving scheme, we have different optimal operation points. We need to enable the topologies working efficient with this technology. Something more, yeah, and something more costs usually, yeah, time to design, time to implement, and also to understand. And if I think about software, you know, this is something which was really often not discussed at all, because you know, everybody knows how to implement the LC or DB VNR rectifier. This is like, I would even say it's kind of common understanding for everybody. But to run it operational and tune to the new use cases, this is a topic. Let me give you an example from electrical vehicles, power conversion. So in the primary scope, you will see, so on board charger is a AC to DC converter, nothing special, yeah. But it is super special because the AC line is not fixed. So we have 230 single phase here. We have 3-phase Europe. We have single phase, split phase US. We have Japan, China. We have India, and nobody can really ask the EV driver to limit the AC cable to only 3 meters, right? So you will not buy such a car. So if you look, even running in Hamburg or Munich, doesn't really matter. You see 20, 30 meters of AC cables from a garage and so on and so forth, right? So so it's not easy. And why I believe the software is a good direction to investigate, because the software give you it will give you some interesting views of the power conversion. So finally, you can start to tune. You can start to tune operation point where you see, look, something is wrong, right? So something may be tuned in live operation. So sometimes we talk about preventive maintenance in that scope, but I really see this as a kind of an future loop optimization topic where even the semiconductor experts will definitely need to have a look in the software, how they enable potentially new algorithms running optimally with the technology AB, JFET or Microchip SiC, doesn't really matter. So we all in the same boat. But what customers really look for in future is a bit more software enablement there. And I'm definitely believing in it. And if you go even further in direction gallium nitride, we start to operate in the megahertz domain, which definitely needs some specific software investigation. And that's why I would believe that there will be more such system topics coming. So not isolated transistor or power device focus, but also a more system enabler. Everybody's talking about AI and similar topics. But this is for sure a big topic in the power conversion, not only for optimization, for maintenance, for everything. And I think we have to work in this direction, very clear.
Yeah, I think remote monitoring is one of the very important subjects. I see that my solar panels and the whole system is remote monitored by the company who put it on my roof. So I think in these areas, we need more software support to have a safe and secure feeling about what's ongoing.
Yeah, I really think, you know, electrification, right? Just electrification in general. You need the hardware, but you need the software. You can't, you know, you can have great hardware, but if you don't have the software behind it, then it's just switching devices, right? And if you have all the software, but you don't have the technology of our devices, then you need to be able to operate efficiency at all parts of the conversion, right? So really, they do go hand in hand, and we really need to be able to, you know, put the software with the hardware to optimize the solutions. It's very important.
Yeah,
I fully agree at that point.
If you start looking at EVs going to you know, steer-by-wire, drive-by-wire, autonomous vehicles, safety is becoming a bigger and bigger concern. And so you're seeing even in the low voltage system a lot more focus on eFuse and the zonal architecture. But also in terms of the high power conversion, we're seeing more in terms of state of health monitoring, like you had mentioned. Maybe there'll be some algorithms that are monitoring the RDS on or the gate threshold voltage or different aspects of the device that are reported back, you know, over the air. So you have that data and you can understand the reliability and the performance of these systems. So we typically think of state of health for batteries, but I think we're also going to see it more and more for the power conversion stage. And also, when we look outside the EV and look at the grid modernization, having a reliable and resilient grid, that's important. Being able to have the software in place to monitor the state of health of the systems and being able to recover if there is a fault.
Thank you, gentlemen. We are coming to an end with our SiC session?
And not totally, I think. I think there are 2 questions left, aren't there? Am I right?
Holger, are there 2
Because
questions? It's a question if we continue now, Holger. Then let's continue.
I think,
Holger just saw the time and
yeah, we got 4 more minutes to go because the
so
ruggedness
we
is
can
very
push
important. And Ehab already mentioned it to some extent, but maybe he can give us a 1-minute statement regarding that level of ruggedness which is required in order to achieve the safety which is really needed, in order to handle the electrical stress during a short circuit. And especially when considering the high current in the system's parasitic inductance. We talked about the energy in terms of voltage, amps, and the time. And now the ruggedness. How long can we handle that?
So obviously short circuit is important. We talk device level short circuit, very important, but it also is kind of limited. When you're talking about battery disconnect systems, battery disconnect switches, you're looking at a large system, a large structure, a lot of parasitics in there. So being able to handle that energy when the device is interrupting a current, interrupting a very high current, there's a lot of energy involved, and protection needs to be put in place to handle and absorb all that energy. But even if there is a snubber or a clamp circuit to absorb all that inductive energy, because it's high voltage, there are some practical constraints when it comes to creepage and clearance. So the power module, for example, with your switching devices, could have a snubber mounted on top of it to absorb all the energy, but there's still some distance there and inductance there. And there's going to be, when a device interrupts a current, there's going to be a lot of stress that it sees. So being able to handle high avalanche current and high avalanche energy, both of those are important for a device in this application, where it does need to be very electrically durable.
Okay, thank you very much, Ehab. So 2 more minutes, I think. Bodo?
Let's see. Hey. To Qorvo, what are the main design constraints that Qorvo is addressing for SSCB?
Yeah, I think a lot of these have been mentioned, but just at a high level, a lot of it's form factor, right? We have solutions, we have panels, we have infrastructure out there, and we have to be able to fit into the existing, structures and the sizes that there are. So that's very important. You need small solutions. You need very fast responses, right? From microseconds to milliseconds down to nanoseconds. You need to have very quick responses, and then of course safety, right? You have arcing, you have the welding together, you have the mechanical contactor inherently provides places of error, places of failure, places of safety concerns, right? And so you have to have the safety and of course just robustness of the devices. You have to have devices that are rugged, that can handle short circuits multiple times, thousands of times. So I think those are the main constraints that we see in a lot of these applications that we're all discussing today, which silicon carbide provides solutions to. So it's exciting.
So, gentlemen, we're coming to a point that we end the session. I just want to mention that we have the Wide Bandgap Conference again at the Hilton in December in Munich at the airport, which is important to know to all of your auditorium and to all of you. And we are strong moving forward to make it happen on the 3rd and 4th of December. Thank you, gentlemen. At that point, looking forward probably to see you in Munich. And the next wide bandgap tech talk would be planned for early April. So that's just for people who want to know what's coming ahead. Thank you so much.
And maybe we will see some of you listening right now at 4:30 in the GAN session, which is also wide bandgap.
Exactly.
You're welcome to participate.